Good day, everybody. Today I want to look at using the inverse Laplace transform for solving differential equations that we use the Laplace transform on. So we're looking at the definition of the Laplace transform of a function at the very top here. Highlighted a little. Laplace transform of f of t, integral f of t e to the negative st dt, and that will be some function of s. There's usually a restriction on s so that the integral converges, like if f is a polynomial or sine or cosine, s has to be bigger than 0 so that e to the negative st makes the integral converge. The inverse transform formula we see here, if you have an f of s and you want to get back an f of t, it's this integral 1 over 2 pi I, limit as t goes to infinity, of gamma minus I t to gamma plus I t, e to the st, f of s ds, where gamma is in the domain of f of s. So if I look at a couple of transforms here, got some here. So Laplace transform of 1 is 1 over s, s bigger than 0. E to the at, Laplace transform will be 1 over s minus a. S has to be bigger than a so that we have convergence. And so on. Sines and cosines, s greater than 0, etc. So let's look at the inverse formula then. Maybe one more look at the definition. There it is, that integral. I'm going to try it directly with some software. I won't go from negative infinity to infinity, whoops, but we'll just look at, well, type it in first. Now there's the general integral in terms of t. This ends up being elliptic integrals. They won't be too useful for us, so instead let's just do a finite integral, not go negative infinity to infinity I, but what I have here is 1 over 2 pi I, and then we're integrating 5 minus 1000i to 5 plus 1000i. It's e to the st. The f of s is 1 over s minus 4. And by the table, we would know e to the 4t, its Laplace transforms 1 over s minus 4. So the inverse transform of 1 over s minus 4 should be e to the 4t. And this integral is being computed very slowly. So most of these I have done ahead of time, so we don't have to wait for this graph to appear. So when we see it, it'll be the graph of e to the 4t, and I'll compare it. It's actually already done. My mistake. Now comes the long wait. All right, so now so there was f of t was defined, as I said, essentially with the inverse transform formula. The f of s I used was 1 over s minus 4. And there we go. And if you compare with e to the 4t, a great match. If I zoom in, there's sometimes trouble, not all the time, but near 0, see a little wobbliness in our function, and there's a relation with the Fourier transform, so I won't go into. So there we go. So e to the 4t is graphed along with, and then in red is the f of t. So it's a pretty good match, and I assume if my limits were actually from negative infinity to infinity, the wiggle would slowly disappear. So another exponential, if my big f of s is 1 over s plus 1/2, then that should have come from f of t being e to the negative 1/2 t. So is this thing computing? So we'll see this again, a little bit of time here, but most of these, oh, here we go. So there's e to the negative 1/2 t, pretty good fit. Again, a little wiggle near the origin there. I'll skip all this. Some others, again, these took a while. 1 over s, that's the Laplace transform of 1. So the inverse transform of 1 over s should just be 1. This would be the integral. See, it's not bad. Maybe if I did more limits, it'd be better. 1 over s squared, the Laplace transform of t goes to 1 over s squared, so the inverse transform of 1 over s squared would be t. That one graphed really well. There wasn't even any wiggle that I could see. Well, continuing, the Laplace transform of t squared is 2 over s cubed. So the inverse transform of 2 over s cubed should be t squared. This one, I don't think computes. I'll give it a shot, but I did. So I gave up on time at some point. I think I'll give up on time right now. And let's look at what we're doing. So again, here's the definition. So if I have my f of s, this integral should give me my f of t. And I know the Laplace transform of t squared is 2 over s cubed. So this inverse transform, if my f of s is 2 over s cubed, I should get back t squared. I could have kept it to infinity, but I went again from negative 1 minus 1000i to 1 plus 1000i. So I need gamma to the right of 0, which I have. And so let's find that integral by changing it using a substitution. So if I look at my limits, you know, I've got u minus 1000i. I prefer that to just be, say, negative u. So if I set s equal to 1 plus ui, then this will be negative 1000, and then this will be to u equals 1000. So that's my substitution. S is 1 plus ui. ds is I du. And so what do we get? So if I put in for s, 1 plus ui, got it right there, times t, s cubed, right there. I du for the differential, so the I comes out. Along with that 2, I might as well bring that out. So we got the 2i over 2 pi I. I'll have some canceling there. If I distribute the t, I get e to the t and e to the iut. So I have that there, and 1 plus iu cubed. I'm going to multiply top and bottom by the conjugate of 1 plus iu cubed, and write e to the iu as cosine ut plus I sine ut. So the denominator, when you multiply by the conjugate, will just get the real part plus the imaginary part squared, and then that'll be cubed, right? So there's different ways to do this. You can, it's the cube of this times the cube of that is the cube of the product, which will just be that. Here's the cube, which Pascal's triangle, whatever. Then if you multiply it out, the real part, I'll let you keep track of that. You know, cosine times 1 and times the 3u squared, I sine times the 2 i's. So we get that would be the real part. The imaginary part, this would be cosine times the 2 i's and the I sine times the 1 and the minus 3u squared. Would be here. It seems to always be the case in the ones I've done. The real part is always even, and the imaginary part is always odd. So then this will go to 0, and then we just have this left over, which, if we like, we can, since it is even, double and go 0 to 1000. So that's the integral I have here, except I don't think I doubled. Let's see, where is it? Again, these didn't work. There's the integral. So hopefully this comes a little faster. It still might take a little bit of time. It's a nicer integral. Well, that didn't take too long at all. So here I kept it from minus 1,000 to 1,000. But that imaginary looking integral, if you do the calculation, you just get this real integral. And of course there's the graph along with t squared. They're both being graphed, f of t and t squared. You can see they're identical. Got one with cosine of pi t. Let's look at this here. This one I didn't type up, very messy, but right. So we're going to use this pointer here. This formula as before. Here I never plugged in real numbers for t, just kept it. So for f of s, again, cosine of pi t, its transform would be this. So I know this should invert to cosine of pi t. So that's going to be my f of s. So put it in, and that would be the f of t. I'll just use gamma equals 1. So I know there's trouble at s equals 0. You can kind of see it like I pi, there'd be trouble, you know, on the y-axis in the complex plane. But anyway, so I'll let gamma equal 1. S will then be 1 plus IU as before. ds I du. So put those in. So e to the st, s over s squared plus pi squared. Limit as u goes to 0. There's the I du. Bring that out. The I is canceled. My limits will then be negative u to u, right? S equals, oops, S, yeah. So, no, holy smokes. Yeah, it's still T, drat, fix it on the fly. I wonder if I had it right before. Everything, everything's fine. Okay, so the limit, should be just u goes from t to negative t to t to make those things. So u goes negative t to t. Fix all these. Anyhow, inside here, again, we've got e to the t, e to the I ut, which becomes cosine tu plus I sine tu. I've got the s over s squared. If I multiply that out, then I get a real and imaginary part. The real part is pi squared minus u squared plus 1 plus 2iu. Multiply top and bottom by the conjugate. So then we have that. The multiplying these together, again, will just be the real part squared plus the imaginary part squared. Multiplying all this, well, I did it in two parts. So first the 1 plus iu, it's 1 times all that. And then iu times minus 2iu will be minus 2i squared u, which will be plus 2u squared. So the plus 2u squared and the minus u squared now gives me a plus u squared. Then for the imaginary part, I've got minus iu times all that, and 2iu times 1. So again, minus 2iu plus iu is minus iu. Anyway, so that's right. And then if I multiply here, cosine times the real part, I sine times the imaginary part, those both end up being real and even. The imaginary part would be cosine times the imaginary part, but this is odd, right? This is even times u, that's odd, times cosine odd. E to the t is just doesn't depend on u. And then the I sine times this is even, that's odd. So the imaginary part only has odd terms, and they will go to 0. And I didn't write them this time. So fixing everything. Oops. I'm just going to leave this in. It's a minor detail. Somewhat minor. There we go. So that's the integral for the cosine. So looking at it here. Oops, that's the square root. It actually continues down here. So here's the cosine. It's not too bad. So this was without doing that substitution. But it did take a while, so I'm not going to run it now. And you see the wiggliness there. Well, here it is. If I go to where I'll do it live, here it is. Should be it. So that was the integral. And it's a little easier to go more accuracy. Well, there's still the wiggle. But perhaps a little better. Anywho. By the way, continuing, this would be sine of 2t. F of s is 2 over s squared plus 4. The sine of 2t, its transform would be 2 over s squared plus 4. So this should invert. And this one graphed pretty nicely. For some reason, t and sine t, they don't seem to have the wiggle there at 0. Whereas 1 and cosine, they've got this wiggle there. All right, so then the last one I will do will be you might know that the Laplace transform of root t is root pi over 2s to the 3 halves for s greater than 0. So the inverse transform of root pi over 2s to the 3 halves, that should be root t. So again, I did the usual substitution, and I could just let s equal 1 plus ui. ds is I du. Then my limits will be u goes from negative 1,000 to 1,000. Bring out the I. Bring out the root pi. Simplify e to the t, e to the I tu over this to the 3 halves. Multiply top and bottom by 1 minus iu to the 3 halves. Expand this. And then there's different ways to do this. I did it as it's the magnitude times e to the I theta, where theta is the arctangent of the imaginary over the real part. So that's how I simplified this to the 3 halves part, right? So a complex number is like a r e to the I theta, and that's the way I did it. And then I could take it to the 3 halves. I got that to the 3/4 because it was 1/2, and so on. The angle was good. The angle was originally between negative pi over 2 and pi over 2. So to the 3 halves, it'll still be between negative pi and pi. Anyway, again, the real part is even, the imaginary part's odd, and there's our final integral. Right, so that imaginary looking integral, whoops, just like every other time, becomes a purely real integral. I mean, there was imaginary numbers, but they always seem to be odd and cancel. And if I look at the graph, here's the graph. I think this one won't take too long. Oops. That's before I did it, so let's just stop it. Here. So here's with my integral. Error. Oops. I need to do with plots. Let's see. All right. So let's redo that. we go. There's the f, and there's the plot. In fact, I'm plotting both, I think. Yeah, no, I'm only plotting f of t. All right. Here's the plot of both, the square root and the function. Well, I'm displaying both. So here's the square. I already did the square root from 1 to 3, and you could change it to 0 to 3, whatever. But you can see, of course, it perfectly matches. So this integral worked out pretty well to become the root t. So how does that help us solve differential equations? Well, just a quick look at a couple then. We'll start with this one. Here's a plot of sometimes called a square wave function. It's 1 and 0, 1 and 0, 1 and 0, and don't know what I do here. I just did it a different way. So here would be the Laplace transform of that. So you'd have to do some manipulation. So there's the Laplace transform of the square wave function because it's periodic. Don't worry about that. And here's a differential equation. I'm not going to run it. It did take a while. But if you do the solution, not sure what this is. Oh, that's the complementary solution. But I just made y of 0, 0, and y prime of 0, 0. So I don't think, well, I'm not sure. Regardless, you get a pretty messy, when you do the Laplace transform, you get something that's very hard to invert. But if I just do the numeric result, then well, you can get a graph of the solution. Right? So we can see the solution even if we don't invert the transform exactly. We can just do it numerically. Similarly, here's one with the triangular wave function. This would be the solution for this differential equation. I'm not going to go through the work there, but this is for the triangular wave function, which is graphed right here. Notice it's similar to sine squared. So I actually compared this result I got by doing the integral, right? So if I take the Laplace transform, solving for big Y, not too hard. Inverting the transform would not be easy. But this is a graph of that integral, like before. And just to see, well, getting the exact. So here's the solution if instead of the triangular wave function, it was the sine squared. And now I'll compare the results, and you can see they're pretty similar. So leads you to believe that the result was pretty good. Obviously, it starts to deviate there, so I need more limits, more accuracy, etc. But it's all possible if you work at it. Maybe do some of that complex simplifying that I did before. Change the integral, get rid of the I by doing that. I wasn't going to do it on this problem. But it just goes to show that if you can take the Laplace transform of your differential equation and solve for the big Y, then you can use the integral transform formula to look at a graph of the solution. So, thought that was neat. Hope you enjoyed, and have a good day. And remember, you get what you pay for.